To find the probability that x is 3, we'll take 1 minus all of the other probabilities added together. So the probability that x is 0, plus the probability of x being 1, plus the probability that x is 2. So we'll have 1 minus 125 over 17,576 plus 1575 over 17,576 plus 6615 over 17,576. So we're going to add these all together first. So 6615 plus, what did I say it was? 1575 plus 125. So that gives us 8315. So 1 minus 8315 over 17,576. Maybe it's obvious what to do next. We just need to get these in a common denominator. So this is the same as having 17,576 over 17,576. That's the same as 1 minus 8315. So what we should end up with is 9261 over 17,576. And that's the probability that x is 3. Okay? Utilizing the complement rule. Kind of a spot check. Does this value seem like it may be right? And again, I would say that it does. So we've gone from 125 over 17,576 when x was 0, up to 1575, up to 6615, up to 9261. So as we're seeing more consonants in our slips of paper, the probabilities are increasing. We're more likely to see more consonants, and that makes sense. So this seems okay. Now, here's the thing to consider. To arrive at this number, it's using your previous 3 probabilities. So if 1 or 2 or 3 of these are wrong, this will be wrong. So your errors will compound. So you have to be very cautious in filling out your distribution using the complement rule. It assumes all of your other values are correct. So if you're confident they're correct, this is a fine method to use. If you're maybe unsure, then I wouldn't recommend using the complement rule. So we can just find this directly, and it's not that bad. So if x is 3, if we're trying to find this like we found the other ones, what does this mean? Well, this means that we have 3 consonants in our 3 slips of paper. So we have a consonant first, and a consonant second, and a consonant third. And that's it. That's the only way to have 3 consonants. So we know this. We know that we take 21 over 26 times 21 over 26 times 21 over 26, and we should get 9261. So 21 times 21 times 21, yep, 9261. And that's the probability that x is 3. So we add that to our distribution. 9261 over 17,576. And there you go. That's the distribution. This is the piece we want. Okay. So it takes a little bit of work. So there's kind of, there are several steps to these types of problems. The first is figuring out, well, what are you even interested in? So what is the random variable? What can change? And here it was how many consonants you have. Second, you need to think about, well, what values could my random variable take on? And it's likely going to be several values. One that's easily forgotten is 0. So it's easy to think about, okay, yeah, I could have one consonant, I could have two, I could have three. Out of three, okay, I'm done. But it's easy to forget, none of them could be consonants. So, say that you forgot about x is 0, and you found these all just like we did, thinking about what the slips of paper could look like, following that same process. Something to check when you think you're done is add up your probabilities. These should add up to 1 if you've done everything correctly. Well, if you added these up, you'd be short by 125. So if your probabilities don't add up to 1, it means you've probably forgotten a value of your random variable. So in this case, maybe you forgot 0, pretty straightforward. That means you had vowel, 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 5 times 5 times 5, and there you go. Okay. So figure out what your random variable is, figure out the values, be careful to think about all the values, and then it's just finding the probabilities. And when I say just, I mean, as we saw, there's more to it. You have to be cautious thinking about all the different ways, the different combinations that you could see these particular outcomes. Now, what I will say is typically the ends of your distribution, so like 0 and 3, those tend to be pretty straightforward. What I mean by that is there's usually only one way to see those particular values. When you're in the middle of the table, like with 1 and 2 here, that's when you have to think about the different combinations. So the consonant could have been first, or it could have been second, or it could have been third. You're probably going to be finding multiple probabilities for those. Okay? So that's that example. So let's do another one that's pretty similar. But we'll go a little quicker because it'll be the same type of process. There's just one slight modification here that we'll discuss. So suppose that the percentage of left-handed people in the US is 12%. We take a sample of 3 people, and we're interested in X, which is the number of left-handed people in our sample. So again, there's big X, that's your random variable. We're counting the number of left-handed people we have in a group of 3. So where to start? Maybe we can just sketch out the probability distribution. So in our group of 3, none of them could be left-handed. 1 of them could be, 2 of them, or 3 of them. Okay. So then we can start thinking about these probabilities. So here's what we know. The probability of being left-handed, maybe I'll call that L. And I'll specify that particular event. And then since we have L for left-handed, I could say L complement is right-handed, but I'll just go ahead and call that R just to keep things a little simpler. So people will either be left-handed or right-handed. And we know that the probability of being left-handed is 12%, 0.12. So that means the probability of L complement, or R, being right-handed is 0.88. Okay, so let's think about the probability that X is 0. So that's this first row in the probability distribution. So translating this means what's the probability that the number of left-handed people in your group of 3 is 0. So in other words, our 3 people will be right-handed and right-handed and right-handed. They're all right-handed if none of them are left-handed. Now, we sort of imagine reaching into the US population. What's the chance that the first person we pull out is right-handed? Well, we were told that that's 0.88. And then what do we do with them? Well, we're not told. Do we put them back into the population? Do we keep them out? Well, in this case, it doesn't matter. So here's why it doesn't matter. Let me put this on another piece of paper. I don't know what the exact population of the US is, but let's assume that there are 300 million people in the US. And if 88% of them are right-handed, that means that we have 264 million right-handed people. So the probability that my first person is right-handed is that ratio. And then let's imagine, which again this is like 0.88. And then let's imagine we do selection without replacement. So we don't put them back. So knowing that the first person was right-handed and we keep them out of the population, what's the chance that the second person we grab will be right-handed? Well, now there's one fewer right-handed people, and there's one fewer person in the US. And what you'll see is, well, this number really didn't change. In fact, this is still pretty much 0.88. So the point here is, it doesn't matter if we're doing selection with replacement or without. Technically, we would be doing it, say, without replacement, and the probability would change, but ever so slightly. It'll change like in the 6th decimal spot or something. So for all practical purposes, the probability is not changing. We have such a large population and we're taking such a small sample that we don't really have to worry about the selection method. So essentially in this problem we're going to assume that the selections are with replacement, probabilities are independent, nothing changes. That's a reasonable assumption here. So what that means is we can just multiply 0.88 times 0.88 times 0.88. Oops. So we get 0.681472. And we're going to leave it like that. Don't round yet. Try to keep as many decimal places as you can. So that's the probability that x is 0. 0.681472. Okay. So then we'll continue. Maybe we know that the ends of the table, the beginning and the end, are the easier ones. So we can look at the probability that x is 3. So same idea. What's the chance that the number of left-handed people we have in our group of 3 is 3? So that means we have 3 left-handed people. Left and left and left. Again, the probabilities remain the same. So we have 0.12 times 0.12 times 0.12. So we get a pretty small number, 0.001728. But again, this was x equals 3. Okay. So now as we move into the middle of the table, we remember, well, there's potentially different ways to see those different outcomes. So what if we are interested in the probability that x is 1? So this means one of our people is left-handed, so the other 2 are right-handed. So that one left-handed person could be first, he could be second, or it could be third. So we have left and right, or right and left and right, or right and left. So he could be the first person, the second person, or the third person. And the other 2 have to be right-handed. And just like in the previous problem, these probabilities, as we find the probability, we'll be using the same numbers, multiplying the same numbers, but in a different order. So when we find 1, we're pretty much done. We can take kind of a shortcut. So let's say that we are interested in this first one, left, right, right. So that's going to be 0.12 times 0.88 times 0.88. So that is 0.092928. Okay. So essentially what we're doing here is we are adding together the same number 3 times. So if we want the probability that x is 1, we can take a shortcut and say that we have 0.092928 3 times. Okay. So essentially what I'm saying here is 2 plus 2 plus 2. You can add those all together and you can get 6, but that's the same as saying you have 2 3 times. Since we're adding together the same number, we can just multiply how many of those numbers we have. And it's kind of a shortcut. So 0.092928 times 3 gives you 0.27878.